And now in 11.5, we'll move into what we call the alternating series. We've established a lot so far. Particular series that we should know about, p-series, geometric series, know their convergence. Whenever we see a series, that could be a solid, somewhat easy integral. Integral test could be an option. We have our comparison test, the regular and the limit comparison test. If they look close, if they're not a p-series or geometric series but are close, we can apply that. And now in this section, this is actually a pretty nice section because we will discuss a pretty nice type of series. An alternating series is considered alternating when as you go from one term to the next. So if I wrote this out, A1 plus A2 plus A3 plus ... in our typical generic way, but what actually happens as you alternate from positive to negative signs. So look at these little three variations I have written right here. The minus 1 to the n, or minus 1 to the n plus 1, or minus 1 to the n minus 1. If you rewrite, if you are able, I should say, if you are able to rewrite the underlying sequence as one of those times something else, this, well, now it just depends on whether we start with a plus or a minus. It would either be b1 minus b2 plus b3 minus b4, and we'd keep going with that alternation. But again, or it could be a minus b1 plus b2 minus b3 plus b4. The next would be a minus. Either one of those, that's what we're talking about when we're referring to an alternating series. So right off the bat, can't use any comparison tests on here. The whole idea of comparison tests were that we always had positive terms. Well, once you introduce a piece like this, well, then obviously we're not just dealing with all positive terms, but specifically these pieces are forcing that alternation, that alternating sign from positive to negative. So that's our whole key, because if we can see a series has that form, then we can apply the alternating series test. It's a specific enough series that it gets its own specific test. And the test says, first we've already established that we have an alternating series. So again, notation, everybody, we've always used the a sub n as that general underlying sequence. In the previous video, 11.4, we had a sub n and b sub n. We used a sub n as the original sequence that went with the original series. And then b sub n was the underlying sequence for the new series that we are introducing. Well, here I'm using b sub n, but I'm using it for different reasons. This is not a new series, a new sequence that goes with a new series. It's just a manipulation on the original. So that when we can think of the series in this form, the minus 1 to a power takes care of the alternating part, and then the b sub n is the leftover underlying sequence. I'm bringing that up because the alternating series test, everything that goes with it, is all about this underlying sequence. So what we can say here, if we have an alternating series, and if b sub n is decreasing, which again, with our sequence notation, b sub n is bigger than or equal to b sub n plus 1, and the limit of b sub n equals 0. Those two conditions, that's enough to say, then the series, the alternating series, converges. One more time, this is another test that only leads to one conclusion. This is a little similar to the test for divergence, I suppose. The test for divergence only said if the underlying sequence limit did not go to 0, then the series diverged. And that was the only conclusion we could make. Similar here. A lot of people make the mistake, if we fail one of these two, then they conclude the series diverges, but that's not an option according to this test. This test only tests for convergence. But I'll quickly point out that's not really going to be an issue. So, doesn't seem like there's much here. Just before we jump in and start doing some problems, I'd like to, actually, let's do a few problems, and then I'll come back and point out why the alternating series test, why it is this simple, why we're lucky enough that if a series has this form, why it is this simple to test that it converges. And then we'll also quickly bring up the idea of remainder again. Remainder is really, really friendly when you know you have an alternating series. But for right now, let's jump right in and let's use this. Do the following, converge, diverge. Again, support your answer. Keep getting these directions. Remember, everybody, I keep saying it, but it's just like integrals. When we learned all the different integration techniques, it was important that you work through each video, work through the homework from that section, get the practice applying that technique so that eventually when all those problems were mixed together, you could first decide what technique would work and then feel comfortable and confident going through applying that. Similar here with all the different series. We're trying to get all the individual practice with all the different series tests, all the different types of series to make good conclusions, to know how to support our answer. But I hope you're also looking at the types of problems, the types of tests that go, the types of series that go that we're using the individual tests on. So that way, when we start mixing them together, you already have that good sense of this is already geometric or P series. And we'll add to that, this is already an alternating series. So let's try the alternating series test. So let's jump right in. Number one, let's look at -1 to the n plus 1. And I have n plus 2 over n cubed minus n plus 1. So looking at that series, and it is screaming out alternating. I mean, this is exactly matching exactly what we see up here. Everything is exactly in the proper place where, we've got the -1 term kicked out in front. So all of this would be the b sub n, the notation that we're using for b sub n up here. Okay, so seeing that it's alternating, well, that tells me it's alternating. The rest of the test is all about this. Oops, I didn't want this to be quite that hard. Let's just make this n cubed plus 1. N plus 2 over n cubed plus 1. So now there's two things we have to confirm here. I'm going to be honest with you. If the alternating series test isn't going to work, it typically fails here. So even though we have both of these to apply, and if we're going to conclude converges, we have to confirm both of these are correct. That yes, the underlying b sub n's do decrease, and yes, their underlying limit goes to 0. But the order we do them doesn't matter. Since, like I said, you don't know this yet, but as we keep going, this normally fails because of this option. So I encourage people to do this part first. Not a big deal if you don't, though, but just to realize I'm not going out of order. It doesn't matter the order. So I set up the limit. Again, the -1 part is ignored. When I'm doing these two, I'm just looking at the underlying b sub n. Well, here, dominant term, n over n squared, n cubed, can simplify to 1 over n squared. That limit is 0. Check. Not enough to make a final conclusion, but enough that we're on the right first step, right? So check. We've confirmed one of these. And just before I keep going, lots of limits, right? When we looked at sequences, all we had to do to tell converging diverge was take the limit, and that's that. But now as we keep going further along, well, we had limits as a part of an integral test at the end, because when we solved that improper integral, we had to set up a limit. So need practice with limits. And then with the comparison test, one of them was the limit comparison test. More limits. Here we have more limits. The test for divergence is a test based on the limit. So as we keep seeing, limits come up all over the place. Sometimes here we want it to equal 0. If we were hoping the test for divergence worked, we'd want this to not equal 0. So it's like, what do you want? What happens? In the limit comparison test, a very different limit, but when that limit equals 0, the test failed. So this is why I keep coming back and saying this is not just a simple matter of conclude, converge, diverge. It's keeping track of everything we've established. What are the tests you're applying? What are the results you need? What are the results you're actually getting? So here, so far so good. We wanted this limit to equal 0, and there was nothing fancy. There was no b sub n plus 1 or b sub n over a sub n. It was just the plain b sub n, not including this part. That's what made this b sub n. Took that limit, we got 0. 2, is this decreasing? Is b sub n bigger than or equal to b sub n plus 1? Well, we already have this as b sub n. Is that bigger than or equal to n plus 1 plus 2 over n plus 1 quantity cubed plus 2? Not obvious, but this is not a comparison test. We said in the regular comparison test, if our inequality was not quick and easy, well, maybe we just want to go to the limit comparison test. But again, what are we doing here? I'm not setting up this inequality for a comparison. I'm setting up this inequality to compare b sub n to b sub n plus 1. So there's my regular b sub n. There's my b sub n plus 1. All right, I can clean up a little bit, maybe before I even cross multiply. That's just n plus 3. This, you FOIL all this out, you'll get n cubed plus 3n squared plus 3n plus 1 plus 2 would make that a plus 3. So maybe you just want to do a little cleanup, but I'm still going to need to do some cross multiplying here. This is not obvious, but this times n plus 2 times all of this. I distributed the n. Now when I distribute the 2, all of that would be my left side. Oops, sorry. This times this. Again, I'm just distributing n times all of this plus 2 times all of this. And I try to set myself up so that I could easily combine my like terms. And now this times this, much quicker and easier to multiply. We get an n to the 4th. Actually, I could just go right here. N to the 4th plus 3n cubed plus n plus 3. And we're just about there. I can cross off the n to the 4ths, subtract 3n cubed, I get a 2n cubed. I don't have any n squared, so I still have a 9n squared here. Subtract n, I still have an 8n. And then if you want to go the other way, here's these little variations. Subtract the 2. Is all of this bigger than or equal to 1? Check, yes it is. And starts at 1 and then just gets bigger. So multiplying and adding this would definitely give me something bigger than or equal to 1. So not bad. The limit was pretty quick. The decreasing part was a tiny bit tougher here. It's not always, this is about as bad as we normally get here. Again, we'll see some other ones, but still not bad. Everything is well set up. Come over here. We can say this converges by the alternating series test. Making our conclusion and including whatever test, whatever it is that we applied. Okay, now let's take a peek at number 2. Again, still sticking with the converge diverge. And now when I look at problem number 2, minus 1 to the n over, let's do 3n minus 1 all over 5n plus 2. Well, one very tiny thing here. This minus 1 to the n, it's technically a part of the numerator, but no big deal kicking that out in front. So that's just a tiny little move, but again, this hopefully is just as obvious as the first problem, that that minus 1 really, really stands out so that this is an alternating series. Whether it's minus 1 to the n plus 1, n minus 1, doesn't matter. It's a minus 1 to a power. That is going to keep giving us that flipping alternating sign. So looking at what's left behind, well, take the limit. Doesn't look bad. Dominant terms. This limit equals 3/5. Does not equal 0. This is why I suggested start off with the limit. This is almost always, not 100%, but for our purposes, for the types of problems we see, if you have an alternating series that diverges, it's probably going to fail at this point. But you can't say that this diverges by the alternating series test. Again, we pointed out when we wrote out the test, that conclusion is not an option for the alternating series test. But what did we just find? We found the underlying sequence doesn't go to 0. Even if you include that alternating -1 to a power, that's not going to change that. So this limit did not go to 0. This series does diverge, but the reason is the test for divergence. Underlying sequence didn't go to 0. If it does go to 0, that's only step 1 in the alternating series test. We still have step 2. But if it fails step 1 here, we actually failed a completely separate test. I mean, again, the idea of fail is very relative. Fail, but fail in that this failure actually gives you a conclusion. The conclusion is that the series diverges. Okay. Number 3. Let's look at 1 minus 1 over 8 plus 1 over 27 minus 1 over 64 plus 1 over 125 minus ... It's been a little while since we've seen this, but a couple of sections ago, it was fairly common. I don't want to say too common, but most of our series are given in this kind of general formula, but we've certainly received series by just getting a bunch of terms in that series. And in numbers 1 and 2, we pointed out the -1 to a power has to really, really stand out. Here, it's just literally seeing the plus minus signs. Whether it went plus minus or minus plus minus plus, we keep flipping signs, so this is definitely an alternating series. So what do we do from here? Well, we do want to apply the alternating series test, but one little issue to go with that, how do I want to phrase this? The one little issue to go with that is that we need the b sub n. So in the earlier problems, it was just get that -1, push that out of the way, and what's left over is b sub n. Here, the plus minus established the alternating part, but thinking about just what's here, that's how we can establish the b sub n. Find the general term for the sequence, for the underlying sequence, ignore the plus or minuses, and that's your b sub n. So hopefully if you're thinking about that, and it's, again, been a little while, but we've had some experience working backwards like this, are you seeing any patterns? Again, don't worry about the plus or minus. We already figured that part out. And it doesn't matter which one it is. I mean, here, if we're starting with n equals 1, it would be a -1 to the n plus 1 or n minus 1 power. This one would actually start with the negative. The other one would start with the positive. But that's not the important point. It's, again, the b sub n's. I hope maybe we're not quite seeing it here, but go further along. 8 is 2 cubed, 27 is 3 cubed, 64 is 4 cubed, and so on. B sub n is 1 over n cubed. If you weren't quite clear what I was saying a moment ago, you don't need the whole setup. That's why I was saying, like, you could keep working this, and well, which one is this part? And in this particular one, again, you need either n plus 1 or n minus 1 to make sure you start with an even exponent to start off with the plus sign and not the minus. That's what I was saying a moment ago. But again, as far as applying this test, this is the only important part that matters. So it's not necessary to do all of this as long as you have this part. And now we're on easy street. That was the hard part. This one works out super fast and easy. This limit is 0, check. Didn't even have to really work any dominant terms. It was just perfect. 1 over infinity cubed. 1 over infinity takes us to 0. The decreasing part, there's your b sub n. There's your b sub n plus 1. Is the inequality true? It is, right? Bigger denominator is smaller fraction. So therefore, the series converges by alternating series test. So again, just to see some random terms, still not the worst. Number 4, just a couple more little things, a couple more problems, little things to point out just to get a little more practice and familiarity. And then, like I said, we'll just talk a little bit about remainder and point out why this test is so friendly, why these series in general are actually pretty friendly. So number 4, let's look at minus 1/5 to the n. Well, I hope, again, I know we're really focusing on alternating series, but don't forget things you already know. That's geometric. Not even that it's kind of like geometric and we can compare. That is geometric. It has a r to the n. Again, I know we kind of preferred initially r to the n minus 1, but that's the only place we have an n. This would be my r value. The absolute value of r is less than 1, so this series converges. But maybe you didn't see that. All right, it's very easy to, again, we're talking about alternating series, so plenty of other people, their move is to do this. Break up that into minus 1 to the n over 5 to the n, so that they could think of it as minus 1 to the n out in front, 1 over 5 to the n, so that they can treat this like an alternating series. And that's fine. We've seen plenty of alternative ways, just definitely want us to realize that certainly still works. But here, there's my b sub n. So what happens to the limit? 1 over infinity, it's a 0, so that's a check. Is 1 over 5 to the n bigger than 1 over 5 to the n plus 1? Again, maybe just like here, maybe you want to cross multiply before you confirm that just so you feel a little better. But I keep hoping, as we work for more and more with inequalities, that we just get more and more practice and see these fractions and say, oh, this is still easy. Same numerator, bigger denominator, smaller fraction. This inequality is correct. So here, we made our conclusion, and that was it. Here, alternating series, just a tiny bit more, tiny little bit of manipulation. Steps 1 and 2 are really fast. Same conclusion, but just again, make sure we include. You say R, you don't have to say converges by geometric series. That's not a test, it's a type of series and it's based on R. So you don't have to say anything extra. Again, we already hold R as a letter in reserve, meaning that it's the geometric series and R is that common ratio. Similar when we use P. You don't have to say by P series. P is letting your reader know you know it's a P series. But here you apply the test, so make that clear. This series converges by the alternating series test. Okay, last one, number 5. Let's look at the series cosine of n pi over n squared. Definitely not obvious. And this is where another reminder, when things are really, really not obvious and you don't know what to do, sometimes writing out a few terms helps. Sometimes that might establish something, point you in a right direction. It might point you that the underlying limit is not going to 0. It might point out something like, oh, hey, maybe I didn't realize that it was geometric, like something like this. Well, in this one, if you start plugging in, you get cosine pi over 1 squared plus cosine 2 pi over 2 squared, cosine 3 pi over 3 squared, cosine 4 pi over 4 squared, ... And it doesn't feel like much is happening, but then when you work a little more, cosine of pi. Thinking about your unit circle, so we're over here. Cosine, the x-coordinate here is -1, so I get -1 over 1. Plus cosine of 2 pi, I'm back to here, and the x-coordinate here is +1, so I get +1 over 4. Cosine of 3 pi, I'm back to here. I get -1 over 9. Cosine of 4 pi, I'm back to here. All this is is a fancy little way to show that we start off saying that -1 to the n is such a key highlight, something that should really stand out. And this is just a funny, clever way to point out that is specifically -1 to the n power. And now that we've seen that, hopefully we won't be fooled by that. I think there's only one problem in the homework, and every once in a while it might come up on a quiz or something like that. But with that experience, like, oh, that looks weird, but once we write it out, because of the nature of what we're getting inside the cosine, we just keep bouncing from the x-coordinate here to here, here to here. So we just keep getting -1, +1, -1, +1. Well, that's exactly what this does. Not quite as pretty. I'm not saying that's pretty, but that, again, we can kind of see and plug it in. You could do something similar with sine, but you have to do this extra +1/2, because sine bounces from 1 to -1 here and here at 1/2 pi and 1 1/2 pi. So when you plug in 1, you start here, sine is -1. Then when n is 2, you're up here, and sine is +1. And you get that same bouncing back and forth. So that's all there is to this one. Just to see, well, that's still alternating. So we're really just looking at the 1 over n squared as b sub n. And you can very quickly confirm that, yep, that limit does indeed go to 0. And yes, that b sub n is also decreasing. So the series, again, converges by the alternating series test. So we've only seen one that actually diverged, but that's fine because, like I keep saying, if you're seeing alternating series, they have a lot they're a lot more friendly in what makes them converge. That all it takes are those two simple conditions, and now let's explain why that's all it takes. So we're going to use our S sub n notation. So we have a series A sub n, which can be rewritten like this. And actually, let's make it one that starts with a positive, so that it literally goes b1 minus b2 plus b3 minus b4 plus b5 minus b6, and so on. So let's think about why this works. The fact that the terms go to 0 and the fact that the terms are decreasing. Well, let's start off looking at S1, right? Now we've kind of moved a good bit past that, but remember, the real way to understand if a series converges or diverges is by getting back to its sequence of partial sums. We warned you about this in 11.2. We start off, you're looking at this a lot, and telescoping series really needed the whole SN process. But then after that, that's kind of used in the proof work, and now we establish these other tests that we can use to make these conclusions. But if we remember that, S1 is the sum of the first term, so that would just add up to plain B1. S2 is the sum of the first two, but now the way we're doing this, I know that this sum is actually a value smaller than this one, because B2 is smaller than B1. So let's actually apply some numbers here so this makes it a little easier. It's like if B1 is 10, well, B2 has to be smaller, and I'm subtracting. So I still have a positive value, but the value here is smaller than the value I had here. And thinking about my sum on a number line, so here is 0, I added B1, and that is equal to S1. But now I subtracted B2. I'm decreasing, so this term is smaller. So when I subtract, I can't go negative. B2 would represent this distance. So when I do B1 minus B2, that is where I get my value S2. And what we just said here, S2 is still a positive value, but it's a smaller value than S1 was. But now when I look at S3, now I take the sum I already had, right? It's literally B1 minus B2 plus B3. Excuse me. It's literally the sum of these three terms, but I already added the first two, and now I would add B3. Well, I know B3 is a smaller term than B2. I know this is all going to be positive, so it pushes this sum this way. And B3 represents the distance of how far we go, what we're adding. And that would then represent S3. Now, this picture is going to start getting messy, so I don't want to keep making marks in here, but that continually happens. The next term I subtract, so my sum gets smaller, but B4 is smaller than B3, so I can't subtract to here. My subtraction is going to put me somewhere in here. And then I add B5, but that term is smaller than the previous. So it's like I go, here is S4, then here is S5, then here is S6, then here is S7, then here is S8, then here is S9. I just keep pushing that sum closer and closer and closer. And that has a lot to do with boundedness and monotonicity. But eventually, that's why we know those two simple conditions will guarantee this alternating series converges. Because every time you subtract then add, you keep adding and subtracting a smaller value based on the decreasing aspect. And eventually, the fact that these terms go to zero, how far you're budging. Again, these terms are literally how far you're moving away from the next sum. You added this total to S2, so this distance from S2 to S3 is the same as the B3 term. So since these terms are going to zero, eventually what you're adding and subtracting goes to zero. That's how we know we're not just stationary, just bouncing from here to here. So like I said, that's not a formal proof, but that's a little understanding about why that this converges, why it's such a simple test, and it has to do with that alternation. The next thing is when you think about Rn, the remainder, well, look at it. Look at what I was doing here. So again, S3, then I'd say this is S4, then S5, S6, S7, S8. So my final sum would have to be somewhere around here. But at every step of the way, remember how Rn works. Rn is the difference between the actual sum and your sequence of partial sums. That's kind of like your error is what we were looking at. And in this case, if S is here, the distance from whatever S term you're up to, whatever point in the sequence, so let's look at this, S1 to S, this distance is smaller than this distance. The distance from S2 to S is smaller than this distance, which is B3. The absolute value of Rn is always smaller than or equal to just the next term in B. Because again, that bouncing, how far you bounce, well, the final sum is somewhere in there. So if I bounce from here to here, going from S3 to S4, that distance would be B4, and that B4 distance is greater than the distance S3 is from here. And then similar S4 is from here. So that's just a cute little way to try, and again, a nice way, as we've talked about, if I have the alternating series, you know, how long until this series has a remainder less than 1 over 100? Well, I would just look at when does 1 over n squared? When is that less than 1 over 100? Do a little work, and I would get n has to be greater than 10. So by the B11 term, after you've done at least 10 terms, your sum would be within 1/100th of the actual sum. So again, that end little part, that's just a little good for your information. Like I said, maybe a bonus problem, no more than that. But I really just wanted to show you a little more so you understand why this works. Again, not a formal proof, just like we did with the comparison test. It's nice to get that deeper understanding because when you're trying to go through and apply these tests, the better you understand the logic behind why the tests work, the easier it is to keep track of what you need to do when you're applying that exact test.